Okay, thank you very much, and thanks to the organizer for this invitation. I am a local person, so they put me at the last day, which I don't mind at all. So I will be talking about some of our result on field-free spin orbit torque switching driven by unconventional spin orbit torque using quantum material. Uh, Okay. As I told, I am from IIT Delhi. These are some of the topics that we work on. Especially our field, our group is working on spintronics, and today I will be talking about spintronics with quantum materials. So before I start, let me discuss one of the very important spintronics concept, which is known as the spin Hall effect. Now, the spin Hall effect is a kind of Hall effect where you pass charge current like this, whereas the electron is unpolarized, and when you pass this current, so what happens is that it get spin splitting like this. So you have one kind of spin going to one direction, the other going to the other direction. So you call this as a spin current. Now this is quite different compared to normal Hall effect, because in a Hall effect you normally apply magnetic field. In this case you are not applying any magnetic field, or you do not have any magnetization, because this is like a metal, heavy metal such as platinum, where you this effect was initially predicted in the theory, later it was observed in the experiment, and this was the first observation using Kerr effect on semiconductor, which was observed, and they saw this accumulation. And the way it is different from the normal Hall effect, as I pointed out, it doesn't require any magnetic field, no magnetization. And the origin of the spin Hall effect is basically related to, there are two kinds of origin, intrinsic and extrinsic. The intrinsic is coming from the band structure, where the scattering from the relativistic magnetic field due to the spin orbit interaction drives this effect. Also there are extrinsic effects due to the scattering similar to AHE and such as side jump and skew scattering. So the reason why you are interested in this kind of effect and recently attracting a lot of interest is because of the fact that you can use this for memory application, what is called spin orbit torque MRAM, spin orbit torque magnetic random access memory. The principle of this can be understood in this way. So you have a non-magnetic heavy metal, and then top of that you have a magnetic layer. Now you pass the current here, the charge current, and because of the spin Hall effect, you create a spin current, which is shown in this red arrow. This spin current then enters through the ferromagnet, and it can exert a torque due to a phenomenon called spin orbit spin transfer torque, which was discovered by Johnson-Susky. And this torque can then basically do two things. Either it can make the magnetization to precess coherently about the axis of this spin polarization, or it can just switch. The switching is what is interested for magnetic memory application. Then you can store and you can build a memory, and this is how you can build. This will be the structure, and this is an emerging technology as right now. You can make a cross barrier structure like that, and the advantage of this compared to the so-called STT-MRAM, where you use two magnetic layers, is that this is much faster, and especially the endurance is much higher in this case. So this is the motivation for this. And however, before we realize that this, we need to improve this efficiency of the efficiency at which you are generating the spin current, and this efficiency is determined by spin Hall angle, which is the ratio of the spin current to charge current. It scales with the spin orbit coupling, and you need to have higher efficiency. But if you look at some literature, and this is now for certain heavy metals where this spin Hall effect is normally observed, such as platinum, which is the most common one, it is only 1 to 2%. Although this is a little bit old literature, and people have observed higher by different ways, but still the value remains lower. So this is one limitation for memory application, and there is way to increase this. One example that I would like to give from our group was that if you use tantalum instead of platinum, and in the tantalum you can actually change the crystalline phase by changing the growth rate, and then you can see a much higher spin Hall angle up to 16% by using a mixed phase where you can see extrinsic spin Hall effect dominating over the intrinsic spin Hall effect, and that leads to higher spin Hall angle. But this is one way of doing it the normal way, but also there is another limitation of the spin Hall effect which actually also need to be overcome before memory application can be realized, and that is arises from the symmetry. So if you look at normal heavy metal like platinum, tantalum or tungsten, where you have suppose you have a case like you are passing the current along the x-axis, then you create the spin current which is flowing vertical, that is along the z-axis, and the spin polarization along the y-axis. So these three vectors are perpendicular, and this is known as conventional spin orbit torque. The problem with this conventional spin orbit torque that if you have a perpendicularly magnetized ferromagnetic air, then in order to break the symmetry, you need to apply in-plane field to switch. So this is a requirement for the because of this spin pole symmetry of the system. So, but there are materials such as 2D metals and quantum metals like the one I will discuss. Here you can see the spin polarization is actually vertical along the z-axis. So in that case, you can more efficiently switch, and you do not need the applied field to switch the magnetization if there is a perpendicular magnet. So this is some of the unconventional spin orbit torque. In our group, we have okay. Before that, let me show some of the reports of unconventional SOT. And in fact, the first talk in this session was on WTE2, and WTE is also interesting for spintronics. And the reason is that it has the broken inversion symmetry, and because of that, this paper they showed that you can generate out of plane spin current. And we have also done a lot of work on this unconventional spin orbit torque over the years starting from 2023 to until now, and we have seen this unconventional torque in lot of different metals, starting from like this is a non-collinear antiferromagnet, 2D material, this is again on normal light metal, and also insulator, magnetic insulator. Recently we have done some work on Kagome antiferromagnet, and more recently we have one article on archive where we have shown this in on 2D van der Waals metal, germanium telluride. In this talk, however, I am going to talk about little bit new thing about how to use non-collinear antiferromagnet for generating such out of plane spin current. So this comes under a category of quantum material, and quantum materials are can be classified in this following way. Like 2D materials also comes under the quantum material, superconductor, topological insulator, and RASPA interfaces. But in particular, these non-collinear antiferromagnets are very interesting quantum material that I will discuss. And one thing before I go ahead, I want to highlight that this conference is mostly about quantum materials, and I saw a lot of talks. People talk about theory of quantum materials, and also they talk about growing quantum material. But not many people are actually trying to use quantum material for applications such as spintronics. So normally if you want to prove that a material is quantum, then you need to go to very advanced facility, synchrotron facility like ARPAs and so on. But spintronics can also, you can prove the spintronics property as an indirect flow of quantum material. So this is that paper here we're talking about, spin current as a probe of quantum material. So basically we can benefit from both, there is one group of people who are doing quantum material fundamental, another group which is doing spintronics. But if you combine, then you can learn from each other. That is what I want to tell here. Okay, now I will go to the metal that I want to discuss, and this is Mn3 tin. This comes, it is a non-collinear antiferromagnet. The crystal structure has hexagonal with this space group symmetry defined like this. And if you look at the C plane of this is a hexagonal symmetry. If you look at the C plane, you have this kind of inverse triangular structure. This is also known as Kagome lattice. And here, if you look at the blue ones, they are actually manganese, and the yellow is tin, and you can see that they are non-collinear. The overall magnetic moment will be 0 because of the arrangement, but however, it is a very complex arrangement of magnetic spins, and this leads to sometimes little bit of tilting of the magnetic moment out of the plane of the Kagome, and often this structure is defined by something called octopole moment that I will be talking about later on. Now, also this is still an antiferromagnet. So, in an antiferromagnet, you expect that there is no anomalous Hall effect, Nernst effect, and magnetoptic Kerr effect. But these three things are normally observed in ferromagnets with finite magnetism. But in this material, despite being an antiferromagnet, you see these three things: anomalous Hall effect, Nernst effect, and magneto-Kerr effect. And this is related to, this is the reason why it's happening is because this is related to the quantum property of the material, which has been experimentally verified by the presence of these wild points near the Fermi energy, and this, because of these wild points, there is a large Berry curvature which drives these effects, and this cannot be explained by, there is of course in the real system there is a little bit of magnetic movement with the manganese, and this cannot be used to explain this property. You need this quantum property to explain this behavior. So, and in 2019, a phenomena called magnetic spin Hall effect was discovered in this material, which is useful for spintronics application. And this effect you can see, look at by looking at this green curve. If you look at the shape of this green curve, this is actually positive sign. As you reverse the field, it should actually change the sign, and this sign change doesn't happen, and this is an indication that it's not because of the spin Hall effect, but because of some new phenomena which they call as a magnetic spin Hall effect. Now, I will go back a little bit also in the literature, a little bit back in 2017, where it was also predicted that this material will also exhibit a normal spin Hall effect apart from the magnetic spin Hall effect. So, this was from the theory, a theory paper. They calculated the spin Hall conductivity for several materials including Mn13, and he found that there is a finite spin Hall conductivity in this material, and for this is arising from the non-collinear nature of this material system. So, we wanted to experimentally investigate this, and before we investigate, there are two reports of this spin Hall angle in Mn13. This was on nanocrystalline Mn13, and this was in polycrystalline Mn13. But there was no report of spin Hall angle in single crystalline Mn13. So, we tried to grow this in our sputtering system. We have a very good sputtering system which can grow high quality thin films. So, we grow this Mn13 films using ruthenium as a seed layer on the sapphire substrate. So, we have a C-plane sapphire, on that we use ruthenium seed, and then we are able to grow Mn13, and these are epitaxial films, films, and this is X-ray reflectivity showing a lot of nice fringes indicating the quality of the film is good. We also check the fact that it's actually epitaxial doing this so-called fire scan, and you can see that we see these 6 peaks indicating the hexagonal symmetry, and that matches with the substrate and seed and the Mn13, indicating we have good epitaxial film, and this is the relation. Also, the roughness is quite low. Also, we check the composition analysis we perform, and we using EPMA, and we found that we have nearly close to the stoichiometry Mn13, but there is a little bit of excess manganese present, and also the distribution of manganese and tin is more or less uniform. There is no not much of segregation of manganese or so whatever. When you do the magnetism measurement, we do see a little bit of magnetic movement, and this is also has been reported in the literature. This is a very small magnetic movement present, and this is there, or it is not fully compensated, you know. Then we did this inverse spin Hall effect measurement, where we what you do is deposit a permalloy layer on top of Mn13, and then you drive this permalloy layer into resonance using ferromagnetic resonance. and then we measure the voltage generated, and this voltage generated is known as inverse spin-Hall effect measurements, and we see the sign change. So this is indication that this is a normal spin-Hall effect, and we study this as a function of thickness, and from this we can determine the spin-Hall angle as well as the spin diffusion length. Now the interesting point is that this value that we found is quite large actually. If you compare to the theory that was I previously discussed, the theoretical value is actually positive. In the experiment we found it to be negative and also quite large. And we think that this is related to the fact that in a real sample, because we have a little bit of excess manganese, so the Fermi level is slightly changing, and maybe that is the reason why, because if you look at the, if you try to calculate the spin-Hall angle, spin-Hall conductivity as a function of shift in the Fermi level, you can see that it is positive in the beginning, but it can immediately change the sign and become very large, and that may be the reason why we are seeing this large and negative value of spin-Hall conductivity. So after that, we wanted to investigate this magnetic spin-Hall effect, which is signature of the quantum material of this of Mn13. And before we did that, this group in Japan by Professor Otani, they investigated this, and they have done some measurements where they saw that if you look at the structure up here, this is the Mn3 structure, and if you, these are the actual orientation of the blue and red of the manganese, but you can describe this entire thing by this octopole moment, which is shown by the yellow. Now what they show that as you change this octopole orientation, you can change the torque acting on the magnetic layer. So there also they have a structure of manganese 13 and permalloy. So they are able to change the torque by changing this octopole moment. So this can be understood more clearly from this figure here. So what they did is that this is the current direction shown by this dotted line, and the octopole moment is this yellow one here, and the blue one is the spin current that is generated. So when they are parallel, in this case is anti-parallel, or here it is parallel, current and octopole moment parallel, you generate a spin current which is out of plane. So you generate out of plane spin current, but when they are perpendicular, like in this case, you generate a spin current which is in the plane. So you generate out of plane spin current when they are collinear, the current and the octopole moment. So this is the observation they had made. So we wanted to check that, and we wanted to use that for switching. So in this paper, they have shown that you can use that out of plane spin current in Mn13 to switch for a very thin ferromagnet. It was cobalt, nickel cobalt here in this case. They are able to switch that using this magnetic spin-Hall effect. So we wanted to check this, and however, there was, so here they explained that this is due to the magnetic spin-Hall effect. Now, however, there was a contradiction in the literature. If you look at this paper here, so they mentioned that this was a investigation where they were just doing the spin torque ferromagnetic resonance, and in this case they mentioned that the out of plane spin current that is generated is not due to the magnetic spin-Hall effect, but that is due to spin swapping effect. Now this is a new effect that arises only from the interface. So this has nothing to do with the magnetic structure of Mn13. So this appears to contradict that previous paper that was published where they claim the magnetic spin-Hall effect. So there is a apparent contradiction between the mechanism of the generation of the out of plane spin current in Mn13. So that is why we wanted to investigate, and in our lab we have this spin torque ferromagnetic resonance technique where we basically apply a current, microwave current instead of microwave field, and then we get this resonance kind of curve, and from this you can fit the symmetric and anti-symmetric line shape, and the symmetric is related to the in plane torque, the out of anti-symmetric is related to the out of plane torque. This is very broadly speaking, but it's much more complex actually. So we wanted to do that measurement. So we did this using by fabricating this kind of devices. We have Mn13 and permalloy, and then you have this coplanar waveguide, and we have, this is the setup how it looks like, and we did this HTFMR measurements. And you can see that here, if you look at the spectra here, example of spectra, and you look at only the symmetric one, that is the blue one, as you change the 40 to 220 degree, that is, we are basically reversing the magnetic field, the sign of symmetric component doesn't change. So this is a signature, there is a magnetic spin Hall effect present in our sample as well. We also verify this at another angle such as here, and we then did it as a function of in plane angle, complete in plane angle. And if you in this case the RF current is perpendicular to the octopole moment, in this case we do not expect any out of plane current to be generated, and in this case we saw that symmetric and the antisymmetric component follow this sin to phi cos phi dependence. Now this is the standard dependence that you observe normally in the platinum and tantalum. So this indicating that you are generating a conventional SOT. But now if you apply the current along the octopole moment as such like this, so you have to make a basically a device where the current is in a different direction, and then we see this additional component which cannot be explained simply. You need the sin to phi dependence, which is a signature of the out of plane spin current being generated. Now, so this is in very much consistent with the magnetic spin Hall effect, and further more, the magnetic spin Hall effect is a bulk effect. So we expect that it will change as you change the thickness of manganese 13, and it will increase. So this is what we also see. This is actually ratio of the torque, especially the outer plane torque with respect to the in plane torque, and we see that this is increasing, and this agrees well with the magnetic spin Hall effect. Because if it was spin stopping, we expect that it will be constant, because the interface effect will not change with the thickness of Mn13. Then we wanted to use this for the switching, and for that we fabricated such a device where we have platinum, cobalt and platinum. So the reason why we have platinum at the bottom is because we need the platinum bottom layer to have perpendicular anisotropy of the cobalt. Then we have this top bottom platinum layer to cancel the SOT coming from the bottom. So because SOT can come from both bottom and top platinum, but they can cancel, and then you can look at the SOT from Mn13. So we optimize the PMA, and we have also checked the XRD and all that to verify that film's quality is good. And then we did this switching measurements, which we have a now very good switching setup where you can do imaging and transport measurements at together. And here is the result. So if you look at here, this is a Hall bar devices, and here we are passing the current is passed like that, and this current is actually increasing here. This is an in plane field, and this is a pulse width. As you can see, this is switching slowly, and it's completely switched. And here, if you change the field direction, you switch other way, which is consistent with the SOT mechanism. Also, you can get the switching even at zero field. So field free switching at zero field also we are able to get the switching. And interestingly, if you say that because there was already switching was already reported in this system Mn13, if you compare our work with what is reported, then you see that in our work the current density, the critical current density required for switching is quite comparable what they had reported, but we are getting this threshold current at a much lower pulse width, whereas here it was 800 microsecond, and also the switching percentage is much higher compared to here. It was only 60%, we are getting here almost 100% switching. And in order to check that this is not due to any heating effect, or we did a lot of control experiment. So first control experiment is that we did this experiment without any Mn13, and in this case we do not see any SOT switching. So indicating that switching there we observed was due to the Mn13. But also you may still say that maybe there is some heating happening, and that the heating is driving this. So we also check the heating, and the heating is estimated heating around 20 Kelvin, but it's not that high. So heating cannot drive the switching. Also I saw the field polarity dependence, so that cannot also explain simply by the heating. We also checked the fact that because this is an antiferromagnet, there can be some exchange bias, and this exchange bias may be also responsible for field free switching. In fact, we checked we could measure the exchange bias at low temperature, but at room temperature there is no exchange bias. So this cannot explain the switching. So indicating that we can basically explain our observation using more or less with the magnetic spin Hall effect. So this is the summary that we have grown very high quality epitaxial Mn13 and we have measured large spin Hall effect, spin Hall conductivity. We observe this unconventional SOT which agrees with the magnetic spin Hall effect, and then we are able to get much switching with better performance, and there is also a little bit of angular dependence of switching that I didn't discuss, which is related to the magnetic spin Hall effect, but a little bit complex, so I skipped that in this talk. Okay, and finally, I thank the students who actually did the work. This is a result of two PhD students, Himanshu and Ram, and also I thank the funding agency. And before I conclude, I like to just put an advertisement that I am editorial board member in this new journal of NPJ Spintronics. So if you are working on spintronics and you are willing to publish any paper, please contact me, because we can offer you full waiver of the article processing charge. And we are also welcoming some prospective article in this. Thank you very much for your attention.
Thank you, Professor Mukherjee, for this wonderful talk. So now we can have questions from the audience.
Nice talk, sir. My question is, in many of your slides, you have mentioned this damping like and field like torques. So, what are the material parameters on which this ratio of these two torques depend? I mean, in some cases, we also need to do some antiferromagnetic switching, and on that cases, my field like torque is also important, as important as this damping like torques. So, what is some?
There is no simple answer to this question because it's very complex. You know, the normally people believe that the damping lag torque is coming from the bulk, spin Hall effect, and the field lag torque is coming from the interface. But there are also reports which report otherwise. So it depends very much on the metal system that you are investigating, and so many other complex. So there is no, I cannot tell that this is what you should do to get higher. It's not straightforward. Yeah.
Any other questions? I saw hands. Have some time for more questions.
Can I ask you?
Yes.
So this, I just like to understand this 100% switching or let's say 60% switching you are talking about. So when it is not 100% switching, what do you mean? There is a separate extra domain, something?
Oh, okay. Let me go there. Maybe I go. Maybe I go nearby. So actually, in the previous paper they did, they didn't do the Moog measurement. So there you cannot see it, right? So they 60% they calculate by looking at the AHE magnitude, the AHE as a function of field and AHE as a function of current. From the magnitude they calculate 60%. In our case, when I say 100%, you can see that current is along this line, right? So everything is switched. So that is what we mean by 100%. If you were a 60%, then this maybe part of this segment. No?
I can see there are some white stripes. Is it?
Which one? This one?
Along the line, along the back.
You mean at this point, or?
Yeah.
Yeah, there is a little bit of here, but this is some artifact of the subtraction. I think there was some issue there, but like in the other case, some other example I showed, it is almost fully switched. Yeah.
Also, another thing that happens when you have the voltage channel like that,
The
current density there is not same as the rest of the channel. So
right. That could have created. Actually, initially I was expecting that everything will switch, but it is not. Only this line will switch.
If you make it smaller, you will see that the probability probably will.
Right. I think Professor Zakir Hussain has had a question. Yeah, that's a very interesting question. The spin Hall angle of tantalum and tungsten is higher compared to platinum. But that alone is not sufficient for application, because what matters is the spin Hall conductivity, because the resistivity of this tantalum and tungsten is higher. So even though the spin Hall angle is higher, the spin Hall conductivity is still higher in platinum. So that's why most people still use platinum. And the other good thing about platinum is that it doesn't oxidize. Then also it doesn't exhibit multiple phases like tungsten and tantalum. So platinum is still the best material.
Resistivity is very low.
Yeah.
But I'm just one very quick question. So when you calculate the conductivity, don't you worry about the interface? Because are you assuming that the whole spin is transported to your ferromagnet? Or
In which case you mean?
when you calculate say sigma SH,
Uh-huh.
the interface does not play a role.
Um,
I'm not familiar with the experiments that you are doing, but
well, I understand your point. So we have measured the resistivity of in the case of Mn3 we measured the resistivity of Mn3, and we also measured the resistivity of Mn3 and permalloy, and for a particular thickness, and we compare the values are. If you use permalloy, Mn3 is like a parallel resistor, and in Mn3 bulk, so we compared the value. It was coming roughly the same. The interface contribution was not that significant.
okay. So if there are no further questions, let us thank Professor Mudi.